The quantum mechanics of absorption spectroscopy. Since motion and light are both quantized, quantized motions may change state by absorbing or emitting light. In this case, the energy of the transition is equal to the energy of light, which is equal to h nu. And once again, bear in mind, the energy of this transition is bound by the fact that photons are bosons. Therefore, the change can only be 0, +1, or -1 quantum states. The electromagnetic spectrum stretches from long wavelength, low frequency, radio waves, microwaves, infrared, visible, red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-ray, and gamma ray at short wavelengths, low frequency. Since E equals h nu, radio waves at the lowest frequency have the lowest energy, and gamma rays at the highest frequency have the highest energy. Each one of these ranges of energy and frequency can excite a different type of quantum mechanical change of state. For example, the microwave region excites rotational transitions. The infrared region, vibrational transitions. And the visible and ultraviolet region, electronic transitions between an atom or within an atom or a molecule. The simplest of these to look at, and the first one to look at, are the electronic absorption spectroscopy, UV visible spectroscopy, or the electronic transitions. In this case, an electron moves up or down, it absorbs or emits lights while moving to either a higher or lower orbital. The same holds true for either an atom or a molecule. All types of absorption spectroscopy obey Beer's law, where A, the absorbance, is equal to a constant epsilon times L times C, where C is the concentration of the solution in variable units. L is what's called the path length, the diameter of the sample cell. Epsilon is the molar extinction coefficient or the molar absorptivity. It essentially relates to the efficiency of the chromophore, or how strongly it absorbs energy at any given wavelength. The units are not absolute. You have to be careful when using epsilons to see what they were measured in, because the units are proportional to the concentration and length units used. Finally, A, the absorbance, is also not a direct measurement, because every single sample is going to be dissolved in a solvent. Absorbance is equal to log of I0 over I, where I0 is the intensity of light passing through the solvent, I is the intensity of light passing through the sample, and you always therefore need a reference of pure solvent. The important thing to note about Beer's law is that it is linear. For any mixture of X and Y, the total absorbance is going to be the absorbance of X plus the absorbance of Y, or the path length times epsilon of X, concentration of X, plus epsilon Y, concentration of Y. Looking further into atomic spectroscopy. Sample preparation. The sample is dissolved and introduced into a chamber. It can be dissolved in concentrated acid, and the acid solution is nebulized and sprayed into the chamber. the sample can then be energetically energized. This can happen in one of two ways. In atomic absorption, light is shown through the sample to a detector. Different light sources are therefore needed for different elements. In atomic emission, the sample is energetically excited by a plasma. Light is emitted to a detector upon relaxation. Atomic emission is able to detect multiple elements simultaneously. Looking further into atomic spectroscopy. Each element has multiple spectral transitions. At high energy, every possible electron orbital transition occurs. Therefore, the pattern obtained is a unique fingerprint. Additionally, splitting of peaks is possible due to what is known as spin-orbit coupling. J, which you have seen before in terms of molecular rotation, is the quantum number for total net angular momentum. For an electron, J equals L, the orbital, plus S, the spin. So let's consider the sodium atom, which at ground state is 3s2, with one electron up and one electron down. Upon excitation, the up electron could be elevated, in which case, for a 3p orbital, L is 1, S is 1/2, and J being 1 plus a half is 3/2. Or the down electron could be elevated, now with a spin of minus 1/2, with the 3p orbital, L still being equal to 1. J is now equal to 1 minus a half is 1/2. This is important because, as you saw, the frequency, J times J plus 1, is equal to Planck's constant of 8 pi squared times the distance. Therefore, two different J values will give two slightly different frequencies. Atomic spectroscopy is used to determine orbital structure. The pattern of the absorbance or emission spectra gives orbital spacing in terms of energy, and the splitting gives the electronic configuration. Atomic emission is extremely accurate quantitatively. One needs to prepare calibration curves based on known concentrations in order to determine concentration of an unknown. Atomic absorption is accurate to 1 part per million. Atomic emission is accurate to 1 part per billion. Atomic emission is used to determine the composition of stars by examining their spectra and seeing what lines are present and what lines are not. Atomic absorption gives valuable information about the structure of the atom. We now look at molecular absorption spectroscopy. As stated, this also obeys Beer's law, where A sub lambda is equal to epsilon sub lambda L times C. Epsilon, the molar extinction coefficient, is a function of wavelength. Any value of epsilon at any given time gives the shape to the absorbance curve. So where there is no absorbance at some wavelength, epsilon is 0, and it increases as absorption increases. The value that is reported in literature is actually epsilon max, the absorptivity at the peak maximum. UV-Vis spectroscopy can be run in one of two ways. It can be run in scanning mode. In this case, a full spectrum yields molecular orbital configurations of a molecule. And if one prepares a calibration curve, the concentration of various parts of a mixture in solution can be quantitatively determined. Because if you remember, Beer's law is additive. Another valuable way to use molecular absorption is through time monitoring at one or more wavelengths. Through this, the kinetics of a given process can be determined. In order to accomplish this, one must first select characteristic, non-overlapping peaks of reactants and product, and then one monitors them over time. As you've seen, absorbance is proportional to concentration. Therefore, the change in absorbance with time is equal to the change in concentration with time will be equal to the rate. With this, experimental data can be curve fit to determine whether a reaction is 0 first or second order, and to determine the rate constant for the reaction. Microwave spectroscopy deals purely with molecular rotations, or the spinning of a molecule in space. As you recall from our quick review of quantum mechanics, the rotation of a molecule is quantized with the total angular momentum J, and the rotational energy is J times J plus 1 times what is known as the rotational constant B, which is two constants, h Planck's constant squared, divided by 8 pi squared, times I, the moment of inertia, which is the reduced mass times the bond radius squared, which is the only intrinsic quantity of the molecule involved in the equation. Normally, the spectra for a microwave spectrum is measured in what are called reciprocal centimeters, or centimeters minus 1. These are actually energy measurements. From fundamental equations, you know that E is equal to h nu, which is the same as Planck's constant times the speed of light over the wavelength. So therefore, 1 over the wavelength, or a reciprocal centimeter, is equal to the energy divided by hc, with the caveat that the speed of light has to be measured in centimeters, 2.998 times 10 to the 10th centimeters. The rotational constant B, h squared over 8 pi squared I, is measured in joules. However, B with a tilde over it is measured in reciprocal centimeters and is equal to h over 8 pi squared I times c, again in centimeters. Another unique characteristic of rotational spectroscopy is that multiple rotational states are occupied at room temperature. This leads to multiple allowed transitions. The peak intensity for any given transition is proportional to the population of that state. Since you are absorbing electromagnetic radiation in a quantized fashion, the allowed changes in J are 0 plus or minus 1, corresponding to the spin of a photon. Therefore, you have an even spacing between any given transition. In terms of wave numbers, the difference in wave numbers between any two adjacent peaks is going to be 2 times the rotational constant. The only difference occurs at the center when you are either going from up to 0 plus 1 or down from 1 down to 0, where the difference is 4b. These 2 branches have names. The P branch is any change of -1 where there's a loss of rotational energy. The R branch is any change of +1 where you have a gain of energy. Microwave spectroscopy can be used in inorganic compounds to find electronic populations. For organic compounds, it is essentially used to find bond lengths. Once again, your moment of inertia, I, is equal to mu r squared, or in other words, it's proportional to the radius. The moment of inertia, as you know, for a linear diatomic molecule, AB, is the mass of A times the mass of B over the mass of A plus the mass of B, and this would be multiplied by r squared. For other types of molecules, the moment of inertia can be found. For things that are called symmetrical rotors of the general form AX3, think ammonia, you now have 2 possible planes. The plane parallel through the top of the nitrogen, in the case of ammonia, that spins the molecule. Your moment of inertia is 2 times the mass of x, r squared, over 1 minus cosine theta, where theta is the bond angle. For the perpendicular plane, where you would be essentially flipping the ammonia, your moment of inertia becomes more complex. The mass of x, r squared, 1 minus cosine theta, plus the mass of x times the mass of A times the total mass times r squared, 1 plus cosine theta. A third common example, a tetrahedral molecule, such as methane. Anything of the form AX4 is called a spherical rotor. And in this case, your moment of inertia is much simpler. Since the center atom, for all intents and purposes, the carbon in methane, does not move as the molecule rotates, the moment of inertia simply depends upon the value of x, and you get a value of 8/3 mx r squared for your moment of inertia. Moving up in energy for electromagnetic radiation, we now come to infrared spectroscopy, or the absorption of quantized energy to change the vibrational state of a molecule. First of all, it should be noted that it takes a great deal of energy to change the vibrational state of a molecule, and more than 99% of all bonds in any given molecule are going to be in the ground state at or near room temperature. Therefore, the spectrum that is observed is essentially the V equals 0 to V equals 1 transition for all the bonds present. You can occasionally get some exceptions. Things that are known as hot bands, where you start at a higher state, V greater than 0, and go to V plus 1. These are very weak, but still present, and essentially show up at a higher frequency. Overtones are also present, where you start at the ground state of V equals 0, and yet can skip to 1 or 2 higher numbers. This is essentially a harmonic, if one would play a guitar, and they were very uncommon. Once again, The spectrum is traditionally measured in energy units of reciprocal centimeters, which, if you recall, that energy is going to be inversely proportional to the force constant for the bond and directly proportional to the reduced mass on either side of the bond. Because of this, the infrared spectrum is split into ranges. You have what is known as the far IR, between 10 reciprocal centimeters and 400 reciprocal centimeters. In this range, you basically have heavy atoms with a heavy reduced mass and a low vibrational frequency, and this is where you will find inorganic compounds and organometallic bonds. The most common, the mid-range, from 400 to 4,000 reciprocal centimeters, is where most organic compounds lie, because this is where your lighter atoms, like carbon, hydrogen, nitrogen, and oxygen, will form the reduced mass, so the bonds would fall in this range. More interesting from a future career standpoint is what's known as the near IR, from 4,000 rather to 10,000 reciprocal centimeters. Technically, these are reserved for organic hot bands. What actually happens is this range is invisible. Glass is invisible to this range. So for quality control, you can send a sample down an assembly line, scan it through the bottle, and you will get the identical spectrum that you would be used to seeing for a compound, except at a much higher frequency. So it is essentially used as a fingerprint region for quality control. When taking an infrared spectrum, one must always prepare a sample. The material that sample is prepared in is called a window, a material that is transparent at a specific wavelength. There are multiple windows available. For the far IR, you have polyethylene from 30 to 720 reciprocal centimeters, or cesium iodide from 200 to 10,000, but essentially clear from 200 to 500 reciprocal centimeters. The mid-IR, which again, most of you are familiar with, potassium bromide is the preferred window material. It is clear from 400 to 40,000 reciprocal centimeters. And if necessary, sodium chloride can also be used, but it only starts at 625 reciprocal centimeters up to 40,000. For the near IR, you can use simple silicate glasses, which are clear from 3,000 to 55,000 reciprocal centimeters, or quartz, pure silicon dioxide, which is generally used for UV visible and fluorescent spectroscopy, from 2,500 to 40,000 reciprocal centimeters. Using these windows, there are several ways of sample preparation, depending on the type of material you have. If you have a powdery solid or a salt, it is generally advisable to prepare a pellet. In this case, you mix 1 part of sample for 20 parts of your window salt, and you mechanically press the mixture between 6,000 and 10,000 psi to create a clear pellet. For other materials that might be oily or waxy and would not grind in with a solid, a Nugel suspension is used. Nugel is a known compound. It's an organic oil that has a wide range of lack of absorption. It's basically a window material in itself. And in this case, a mull is made by mixing 10% Nugel by volume with your material and spreading it between 2 salt plates that are the appropriate window. Theoretically, since transitions are quantized, every single absorption should only occur at one and only one wavelength. However, in the case of all spectra, but essentially we're now looking at infrared spectra, you have noticed that there's actually a line width. The reason for this are several. First of all, Heisenberg broadening. This arises because there is an quote-unquote uncertainty in the lifetime of the excited state. In other words, in a multi-molecular sample, each individual atom may not have been excited at the exact same time. This can be mathematically determined by the width, the delta in reciprocal centimeters, is equal to 1/2 pi times the speed of light, delta t. Heisenberg broadening is the reason why all quantum mechanical spectra, everything that you get from spectroscopy, does have a line width. More specific to IR is the fact that infrared radiation has enough energy to excite vibrational and rotational transitions. As you have seen, first of all, in the vibration, the Morse potential itself, the well in which the bond is vibrating, is asymmetric. Therefore, to form the Morse potential, the vibrational energy is best fit by a power series, where you have V plus a half H nu as your first set, the common quantum mechanical solution, minus nu sub e chi sub e V plus a half squared H nu, plus nu sub e gamma sub e V plus a half to the third H nu, minus nu sub e zeta sub e V to the plus half to the fourth H, plus and minus to a higher power. In reality, to get the best fit, only the first two terms matter. And this term, nu sub e chi sub e, is called the first order anharmonicity constant. Essentially the fact that the bond, since you have different masses and the molecule is rotating, has some wiggle in it. A second reason why you get width is the molecule is also rotating. That provides a torque to give you anharmonicity. But while the molecule is rotating, the bond is also vibrating, which means the length of the chemical bond is not constant. If you recall, the rotational constant for any bond is proportional to 1 over r. However, that radius changes continually during vibration because the bond is not rigid. So once again, you get a power series, which to the first term is your rotational constant h j times j plus 1 minus d sub e h j squared times j plus 1 squared. And in the whole power series, there will be plus cubed, minus to the fourth, and so on. Once again, the math has physical reality. The second order term, d subscript e, is called the centrifugal stretching constant. It is essentially the bond dissociation energy. A chemical bond is not rigid. As it vibrates, it stretches, and like a rubber band, there will come a point where you cannot stretch it anymore, and it simply snaps. That is the bond dissociation energy and the centrifugal stretching constant for any given bond. So in conclusion, what are you actually looking at when you are looking at a quote-unquote IR spectrum? First of all, the actual spectral transition you are looking at is compound. It is a function of the vibrational state, which always comes from the ground state, but any number of possibly occupied rotational states. So that energy T of V and J is equal to a function G of V and multiple functions F of J. Because the molecule is rotating while it is vibrating, you have an anharmonicity. If you look carefully at any infrared spectrum, the first thing you'll note is the peaks are always asymmetric. And also that asymmetry follows a pattern. They are always wider towards higher wave numbers, towards higher energy as the bond bends while it's trying to vibrate. The rotational transitions also add to line width. In a gas phase sample, the classic experiment with HCl gas, the rotational transitions are always clearly seen. However, in a more typical case, when you have a condensed phase material, these rotations contribute to the peak width. For example, pendant groups, groups hanging outside the main chain, always have more vibrational, or more rotational rather, degrees of freedom, and are also going to be wider than any bonds that are on the main chain. This is seen in the classic fingerprint, the OH group peak, which is always extremely wide and easy to spot.